Good afternoon, everybody. Let's get started with the class. For announcements, Lab 4 will be this week, so you have pre-Lab 4 due this Thursday, and then you will perform Lab 4 this Friday. Check out the other upcoming assignments listed on Canvas. My office hours will be right after class if you have any questions, so stop on by right after class. So I wanted to begin today's class with a preview of Lab 4 to show you what you're going to be doing and why it matters. So this lab will be about Thevenin equivalent circuits and maximum power transfer. You will build a circuit that looks like this. So you have a few resistors in this circuit. You have a couple of voltage sources. You have a couple of terminals between which you are going to determine the Thevenin equivalent. And then you're going to connect a resistive load and figure out what does that load resistance have to be for maximum power transfer. And you'll see that work. The theoretical plots I showed in class, you'll see it work. You'll see those work in lab. Okay, so a couple things to point out here. There's no connection right there between those two resistors. You have a couple crossing resistors here that you have to deal with. You have a couple voltage sources here, and one voltage source has a positive value. So V1 is node voltage, positive 3.5 volts. And then I have the way this voltage source is oriented in the bottom left, you have a negative 4 volts voltage source. So that makes V2 a negative 4 volt node voltage. So you have to figure out how to do that. You did this in, I think it was like lab 1, where you connected voltage sources together to create a negative voltage at one node. Notice that you cannot dial in, you can't enter in a negative voltage into the power supply. So go back to that lab, you'll figure out how to put in, if you don't know how to do it already, a positive 4 volt voltage in, and then switch these polarities and create a negative 4 volt node voltage at V2. Anyway, that's the circuit. Between terminals A and B, you're going to be calculating the Thevenin equivalent and actually building the Thevenin equivalent and showing that the Thevenin equivalent behaves just like the original, more complicated circuit. Okay, so during the pre-lab, though, you're going to calculate the Thevenin equivalent. Okay, and then during lab, you're going to determine the Thevenin equivalent from measurements. So if I didn't show you this circuit, if I just put this circuit in a box and just exposed terminals A and B, and gave you a few resistors and a voltmeter and an ammeter, you could determine the Thevenin equivalent, actually with just a voltmeter and ammeter. You could determine the Thevenin equivalent from measurements, and we're gonna see that. But in this case, you have the internal circuit. So for the pre-lab, you will calculate that and then compare two measurements. So here's that circuit. You're going to connect a load. This is the load resistor. It's external to that original circuit. And you're going to determine VT, the Thevenin voltage, by measuring VOC. So what that means is don't connect anything. Don't connect that load resistor to the terminals. Just measure the voltage between A and B, and that's the open circuit voltage. Then you're going to apply these resistors to the different resistor values to the terminals A and B. And you're going to plot the voltage across the load, VL, versus the current through the load, IL, for various values of the resistor RL. And then you can determine RT based on the slope of VL versus IL. Remember, this is how we defined Thevenin resistance in class. It was the slope of this line. So remember, this was out of the slide that I showed you when we talked about Thevenin equivalent circuits. I put 3 dots on here. You're going to have more than 3 dots, and along that line, it's going to form those dots are going to form a straight line. That slope, right, is negative RT. Okay, so you're going to get something like this. These are my measurements with the numbers on the axes removed. This is VL versus IL. You get, a pretty nice straight line there. And if you calculate the slope, that's negative RT. And then you can create your Thevenin model based on the open circuit voltage and the Thevenin resistance you calculate from the slope of this line. Okay, and then you're going to determine, well, where does maximum power transfer happen? You're going to see that from measurements. You're going to calculate and plot the power for various values of IL. You're going to calculate the power versus RL, not IL, RL. You're going to calculate the power using the Thevenin equivalent. So you've determined the Thevenin equivalent, and then you're going to calculate using that Thevenin equivalent. Well, what if I connect different values of RL? I get a power. You're going to plot power versus those RL values. And when you do this, you're going to see something like this. So here's power versus load resistance. And the my calculated power is in red here. Right? So you're going to use the Thevenin equivalent to calculate the power. And then for measurements, I determine the blue line. You could say, hey, they match up pretty well. And you could see where maximum power transfer happens. You know from class where that's going to happen on this plot. So you'll see that work in action in lab. Okay, so that's the point of lab 4, Thevenin equivalent circuits and maximum power transfer. Okay, let's jump forward talking about RC circuits and RL circuits, or in general, first order circuits. And I want to bring you back to the last slide that we showed during the last class here. Okay, that should be it. Get my arrow on the screen if I can. Okay, so we talked about the transient response of first order circuits. You have a starting value. You have this time varying value of, in this case, voltage that looks like an exponential rise or an exponential decay. And then when you're converged to 99% of your final value, we're going to call that value steady state. You're almost DC there. It's changing just a little bit, but you're 99% of the way there. We talked about defining the time constant. So all of your first order responses are going to have this characteristic, or your equations you derive will have e to the minus t over tau. It's an equation. You'll have an equation that has this term in it, right? It may have like e to the minus 100t, but you can figure out what tau is based on the coefficient of t in the exponential. So tau is the time constant in units of seconds. It tells you how rapidly does this voltage converge from one value to almost another value. And then at 5 time constants, that's where we say the voltage has reached a final value. We call that final value steady state, right? The circuit is in steady state, or you have reached a steady state value after 5 time constants, okay? So that's where we were last time. And you can have rising transients or falling transients. They may or may not start out at 0. They may or may not end at 0. They just start at one value, go to another value for these problems. Okay, so let's talk about determining the time constant. Okay, so we looked at this circuit. We used the general way to solve for the voltage across the capacitor by writing a KCL at this upper right node in a previous class, right? We wrote a KCL up here. I didn't have values in, but you could put values in, and we determined what is VC of t before and after that switch closes. And we determined this. We said VC of t is 0 for t less than 0, and it's Vs minus Vs times e to the minus t over Rc for t greater than or equal to 0. Okay, so if I plug in values that I just took some typical values, 12 volts and 1 k ohm resistor and 10 microfarads, I can plug in the values and I get this equation here. Okay, so you can determine the time constant from that exponential term. So right here I have e to the minus t over RC. I can equate that to the form that I had on the prior slide, e to the minus t over tau. And you could just look by inspection, right? If you replace tau with RC, you get the same equation on both sides. So tau is equal to RC. Okay, so that's a big takeaway here. For an RC circuit like this, right, that looks exactly like this, okay, tau is equal to RC. There are other cases where, like a parallel RC, you'll see, but where you get tau equals RC. But but I want to point out here that this RC applies to this circuit with one resistor, one capacitor in series. That's what we derived. You know it works there. Later, I'll show you what happens when you have multiple resistors. And we will use this. I'll show you. But if you have this numeric equation, you can look at this equation and you can figure out, oh, what's the time constant? Well, you take that exponential and you equate it to e to the minus t over tau. Right, so you could see, just by inspection, tau is equal to 1 over 100. Okay, you could take the natural log of both sides and solve that equation, or you could just look at it and see if you replace tau with 1 over 100, you get one side equal to the other. So that means that the time constant, if I have the circuit with a 1K ohm resistor and a 10 microfarad capacitor, if using those values, I get a 10 millisecond time constant. This gives you an idea of what the transient plot would look like, right? From changing from one value to a steady state value. Here's the transient. Since we have a tau of 10 milliseconds, and we know that at 5 tau, we reach steady state, then just kind of, even eyeballing on this plot, you could tell, oh, right there, that's where we reach steady state. And if you look at the time constant, you could say, well, the 5 tau, that's 50 milliseconds. And indeed, that just by looking at the plot, you could see that's where it converges. In theory, this is still changing after 50 milliseconds. It's not changing all that much. It's within 1% or it's 99% of the way there. So it is still changing. But for all practical purposes, we will consider this DC to the right of 5 tau. Okay. All right, so that's how you can use the equation. You can look at an equation that you've derived and determine the time constant. How about determining, like you have a circuit and you just want to know the steady state values? Let's talk about how you do that. Okay, so after a circuit has reached steady state, and think after 5 tau, we can make some simple assumptions about the circuit to analyze that circuit and then solve for voltages and currents in the steady state, right? So what you have is you have a circuit that might have a switch in it. And you say, okay, I'm going to throw that switch one position or another. I'm going to have a sudden change in the circuit. And then I want to let the circuit settle down to a steady state, like wait a certain period of time, enough time. And I want to determine the voltages and currents after they've stopped changing. So you'll see in homework problems, you'll see, find V1 in the steady state, or find I1 at steady state. That's what that means. You have a sudden change, you just wait a while, and then when all the voltages and currents have stabilized, you determine those values. Well, there's a pretty straightforward, simple way to do this. What we can do is we can replace a capacitor with something and an inductor with something in steady state to make the analysis fairly easy. So this is just the schematic symbol of a capacitor with voltage and current indicated. And you know that I is equal to C dV dt, right? That's just how a capacitor works. That's the current and voltage relationship. Okay. So when you reach steady state in a circuit, so this capacitor is in a circuit, you reach steady state, the voltage is not changing anymore, right? Because everything's steady. The voltages are steady. They're DC. So dV/dt, if V is relatively a constant, dV/dt is 0. So that means I of t is 0. So what you can do is once you assume you have reached steady state in a circuit, you can replace the capacitor with an open. An open also causes I to be 0. Okay, so if you're asked in this circuit, calculate voltages and currents, maybe there's a capacitor in there, in the steady state, then you take all the capacitors and you replace them with opens, right? Because both of these on left and right here of this equal sign in the steady state cause 0 amps to flow, okay? And then for an inductor, let's look at the relationship between current and voltage for an inductor. V equals L di dt. Okay, so in steady state, I is not changing. All the voltages and currents after 5 tau have reached steady state. Someone asks in the chat, is it always 5 tau or is it case by case? For a first order circuit, assuming you define steady state as you're 99% of the way there roughly, it'll always be 5 tau for a first order circuit. Okay, you will reach steady state at 5 tau. And then after 5 tau, you have roughly DC. Okay, so after 5 tau, di dt is 0. So L times di dt is 0. So the voltage is 0. So how do you make 0 happen between two terminals instead of using an inductor? You can use a short. So in the steady state, you can take that inductor, pull it out of the circuit, on your schematic, and replace it with a short. Okay, and so we'll do an example of this, but that the basis, this is the basis for the analysis when the question is determine these values of voltage or current in this steady state or at steady state. Replace capacitors with opens, replace inductors with shorts, calculate those voltages and currents. All right, so why would you want to do that? Well, remember, I said there are two approaches to solve for voltage or current in a first order circuit. One approach is the general approach, write a differential equation, solve the differential equation. The second approach is the initial and final value approach, where you will use steady state values. Okay, so that's why we're looking at this. And I think that second approach is often easier. Okay. All right. So let's switch over to the whiteboard and we'll do an example steady state problem. So this, by steady state example, I mean you're going to be calculating a value in the steady state. So let's suppose you have this circuit here. You take a voltage source. It has some DC value, Vs. Let's give it a value, 36 volts. And we attach a switch that closes at t equals 0. And then let me have an inductor here. And I'm going to put a capacitor. I said we're only going to deal with, in this class, first order circuits. I'm creating a second order circuit, but it doesn't matter for this analysis. You do the same analysis for first order or second order circuits for steady state. So let's put an inductor and a capacitor in here. There's a resistor. Let's see. So let's make this L 0.1 henries, doesn't really matter. Let's make this capacitor 1 microfarad, doesn't really matter. And actually, let me put another resistor in here. I'm going to put 2 resistors to make this more interesting. So this is R1. Let's make that 8K ohms. And this is R2, and it's 4K ohms. So there's the circuit. And let's suppose we want to find the voltage across the capacitor, Vc of t, at steady state. Okay, so that's the problem. So the way we indicate steady state, we often say for t much greater than 0, or t much greater than whenever the switch closed. So if t is 2 seconds, right, the switch closes at 2 seconds, you would say for t much greater than 2 seconds. Whenever you see this, this is an indicator of steady state. So I'm going to say for t much greater than 0, let's redraw this circuit here. And I'm going to redraw it, replacing the inductor and the capacitor with their equivalent values, their equivalent circuit elements at steady state. Okay, so the source stays the source. It's still a DC 36 volt source. Okay, so that's that. And then we have a closed switch. Right, so this switch is now closed because we're past t equals 0, long past t equals 0. The inductor, as I showed on that last slide, becomes a short, right? So that's because L di dt is 0 volts for that inductor. The capacitor becomes an open, right? And that's because the current I is equal to C dV dt. dV dt is 0, so this is 0 amps. And then we have a resistor, 8K ohms. And we have this other resistor, R2, 4K ohms. There's a K in there. So this is the new circuit. So at steady state, this is what the circuit behaves like. Even though there is still an inductor here and there is still a capacitor here, the inductor now looks like a short at steady state, and the capacitor looks like an open at steady state. So this is the new circuit. I have a 36 volt DC source connected to 2 resistors that are in series. Remember that if 2 circuit elements have the same current flowing through them, they are in series. So I have a voltage source across 2 series resistors. I can use voltage division. Right, so voltage division will let me do this. Well, I'm trying to find this voltage, Vc of t. I should have written that first to recognize that we're trying to find the voltage across that resistor. Well, really, we're trying to find the voltage across the capacitor, but that's the same as the voltage across R1 in this case. Okay, so voltage division says Vc of t is the voltage across the series resistances times on top of this ratio goes the resistance across which I'm trying to find the voltage, and the bottom, the sum of the series resistances. So that's VC of t equals, what is that? 24 volts for, comma, t much greater than 0. So we have not determined what is VC of t between t equals 0 and sometime much later, right? Much later. We haven't determined that. We don't know what that response looks like, but we do know this, that eventually, and this is not a first order circuit, so we're not using, the RC time constant. But we do know that eventually this circuit converges to a steady state value, or the values converge to steady state. And if you leave this switch closed long enough, then VC of t will be 24 volts. Okay. So that's how you solve problems when the question is, in the steady state, determine VC of t, determine the current through the resistor, determine voltage across R2, right? You would use the same circuit in steady state. Okay. All right. So let's make this useful. Let me show you how to use the steady state values to determine the solution of a first order circuit. So I've shown you this before. I said there are two approaches to solve for a voltage or a current in a first order circuit. We did this. We did the general approach. We said, okay, write a differential equation, solve it. And then the second approach we're going to talk about now, it's the initial/final value approach. We're going to perform steady state analysis, which we just did, and then determine the time constant, which we just talked about as well. And then we're going to look at the form of the solution and plug some values in. Okay, so we did this. Talk about this next. Okay, so here is how to solve a first order circuit, solve for a voltage or a current that changes, that is a transient value, using this initial value and final value, which I also call a steady state value. We also call it a steady state value. So here is the form of a voltage in a first order circuit that changes exponentially. And I differentiate. I say, well, not all voltages change exponentially, because if you turn a voltage source on, a DC voltage source, if you turn a DC voltage source on, it just goes from like maybe 0 volts to 6 volts or whatever. That voltage doesn't change exponentially. But the voltage across a capacitor or a resistor, or the current through a capacitor or through a resistor can change exponentially depending on the circuit. Okay, so if you have a voltage that changes exponentially, this is what form it will have. V of t is going to be VF plus the quantity VI minus VF times the exponential e to the minus t minus t naught over tau. So the step change occurs at t naught, at t0 here. So we've been saying, well, the switch closes at 0 seconds. If the switch closes at 2 seconds, T naught will be 2. VI is the initial value. That's the value right at the start of the transient. That's the initial value. at t equals t0 plus. So right after, let's say, a switch changes, that's the initial value. The final value is the steady state value. That's the value to which v of t converges. And then tau is the time constant that we talked about. Currents can also change in this way. So just replace I with v, and you get the same equation, right? T naught is the time when the step change occurs. I initial is the value of the current at T naught, just after T naught. I sub f would be the final value of current at steady state. Tau is still the same time constant. So all of the time constants that you use in the equations for finding voltage and current are going to be the same for a given circuit. And for an RC circuit, we showed that based on solving the differential equation and getting the result, we saw that tau is equal to R times C. So that's the time constant of an RC circuit that has a series resistor and capacitor. If you have an RL circuit, just replace the C with an L. If you solved the differential equation, let's say, maybe current through the inductor or something like that, you would find that the time constant in the exponential argument would be L over R. So that's the time constant when you know the series inductance and resistance. Okay, so that's just something to note. We could prove that, but you can accept that for now. Maybe look in the book if you want to see the derivation, but this is what it will wind up being. Okay. And so what I'm going to do now is actually implement this. We're going to do an RL circuit. We're going to solve an RL circuit, and I'm going to use this approach. So I'll write this down again on the whiteboard. Okay, so let's do that. Okay, let's get rid of this example. So let's solve an RL circuit. So this will be an RL circuit example. And we're going to solve this circuit using, and when I say solve the circuit, we're going to determine a current and a voltage using initial and final values. Okay, so here's the circuit. We take a 100 volt voltage source. And we connect that to a switch. We connect that to a resistor and an inductor. And that's it, just a series resistor and inductor. So this resistor value is 50 ohms. The inductor value is 0.1 henries. Okay. And let's find the current through the inductor. I of t. And let's find the voltage across the inductor, V of t. Mhm. Okay, so we're going to use this initial and final value approach. So what that means is, let's find current first. I of t is going to equal the form that I showed on the slide, I sub f, right? IF plus II minus IF times e to the minus t over tau for t greater than or equal to 0, because I'm going to cause this switch to close at t equals 0. And we know from what I told you that tau is equal to L over R. So someone asks, does this analysis method work if you have the inductor in parallel with another resistor? I'm going to say yes with an asterisk. I'm going to show you how to, any circuit that you have can be formed as a series resistor and inductor, okay? And then you can use this approach. So I'll show you how to do that. But for now, let's just assume we have a series resistor and inductor. All right, so we solve for two different time spans. Before t equals 0, because we need an initial value, and then long after t equals 0. So let's start out with for t, let's less than 0, less than 0. So for t less than 0, for t less than 0, we have no current flowing through the inductor, right? The switch is open, so no current can flow through that inductor. So I of t equals 0. What we really want is, okay, what happens right after that switch closes, right? We really want the initial condition II, which is just right after that switch closes. What is the current? Well, this is similar to the voltage across a capacitor. What happens in an RC circuit with the voltage across a capacitor, except this is the current through an inductor. So we know that for t less than 0, I of 0 minus is equal to 0. What we care about is, what about I of 0 plus? What is that? Because that's II, right? Well, right at that instant of time, okay, a little interval of time, when you go from 0 minus to 0 plus, the voltage for across the inductor is L di dt. Okay, this says that current through an inductor cannot change instantaneously. In other words, you can't have, like, versus time. You can't jump from one current to another instantaneously. You can have some kind of smooth transition, but you can't have like a sharp negative infinity slope or a sharp positive infinity slope, right? Because that would take infinite voltage to do. So if the current is 0 right before the switch closes, then the current is 0 right after the switch closes. And so that is II. Okay. So for this circuit, I sub I equals 0. That's one of the values we need here. Next, we try to find the steady state value of current. That's IF. So for t much greater than 0, how much greater? Much greater than, well, 5 time constants or later. Okay, so we close that switch and wait a while. So what that looks like, the new circuit in steady state equivalently, we have Vs, which is 100 volts. We have the switch that is closed, right? The switch is closed. We have a resistor, 50 ohms. And then we have an inductor, and the inductor in the steady state can be replaced by a short. So that's what the circuit behaves like when all the values are DC. We're in the steady state. Well, so you could figure this, well, this is I of t now, coming down that way. And so what is that? Well, you have a 100-volt source over 50 ohms, right? So this is just 100 volts across 50 ohms. You want to calculate the current, you use Ohm's law. 100 volts, just put 100 over 50 is equal to 2 amps. For t much greater than 0, and that means IF, the steady state value, is 2 amps. So now we have the initial value and the final value. We need the time constant. So someone says, what's the case where I is not equal to 0? That's a good question. So imagine this. So don't change the problem. But if I had put another resistor here, right, another resistor like that, then this equivalent resistance would be, I don't know, 100 ohms until I close the switch, and then it changes to 0 ohms. And so II would be something, and then it changes to something else, right? So you could do that. Okay. So now we need to find tau. And tau is equal to L over R, which is L is 0.1, R is 50, and that's equal to 0.002 seconds. So what's that? 2 milliseconds. 2 milliseconds. All right. So we could now we can plug these numbers in. We plug these values. This is tau, IF into the form of the solution. So I of t equals IF. What was that? 2 plus II minus IF, 0 minus 2. E to the minus t, right? Minus t naught, but t naught is 0. E to the minus t over tau, 0.002. Okay. So then you wind up with, we just do some simple math here. I of t equals 2 minus 2 e to the minus 500 t, or t greater than 0, greater than or equal to 0 actually. Okay, and t greater than or equal to 0, this even handles the case where t is much greater than 0, because if you take, make t 1,000 seconds or whatever, you get e to the minus 500,000, which is going to be almost 0, which means I of t should be 2, and it is. Okay. Okay, so that's how you find I of t using this initial and final value approach. I used really 2 steady state values, I'll tell you, because really before the switch closes, I have a steady state. I have all DC values. And then after the switch closes, something happens with the current and the voltage, and then I converge to a steady state value. And then in between, I can use the form of the solution, the initial value, the final value, and the time constant to find I. So let's do this. Let's next find V of t. Okay. So this was the I of t solution. This is the V of t solution here. Well, this you'll see is a little easier. We know I of t, so if we could only find V of t from I of t, and we can, V of t is equal to L di dt. That's the relationship between current and voltage for an inductor. And we know all those values. We know I of t and we know L, so we can just calculate V of t. So V of t is equal to L 0.1 times the derivative of 2 minus 2e to the minus 500t. So what's that? 0.1 times the derivative of 2 is 0. And then we have, let's see, minus 2 times minus 500, right? Because we have minus 2 times minus 500 comes out e to the minus 500t. So I get 0.1 times 1000 e to the minus 500t. So V of t is 100 e to the minus 500t. Okay. So we calculated V from I here. Let me point out something here. If we plot I of t versus time, that says I of t. I of t versus time. And we plot V of t versus time. Yeah, someone asks, how do I get the minus 500? Minus 1 over 0.002 that's where the 500 comes from. Okay, so we have I of t. We know it starts out at 0. The switch is open. And then you have this exponential rise. And it's steady state at about 2 amps. Okay. And this happens at 5 tau, which is 5 tau, and that's 5 times 2 milliseconds, 10 milliseconds. So that's what that plot would look like. Okay, so that makes sense. Like we have this change right here from, there's no instantaneous step change of current, so that makes sense. And then we get this convergence and then steady state. For V of t, that's a little different. V of t before t equals 0 is 0, right? I think you can see there's nothing happening here. There's no current through the inductor, no change in current, so V of t is 0. But then right at t equals 0, I get 100 e to the minus 500 times 0. I get 100 volts right there. And then if I plot this, right, if I go off to infinity, e to the minus 500 times something big, the e to the minus something big becomes 0. I get this converges down to 0, right? So if I can get my time constants right here, you're going to see this behavior, something like that. That's what the voltage is going to do. So notice that I get this step change in voltage right at t equals 0. And that's okay because I is the integral of V for an inductor. You can integrate across this step change without having any values blow up to infinity, right? If you take a derivative of an infinite slope, well, that's bad. But you can integrate an infinite slope, and that's fine. In fact, if you integrate this, right, multiply by 1 over L, you get this. So that's what would happen there. But I wanted to point this out because it is totally fine to have a step change of voltage across an inductor, right? You cannot have a step change of current through an inductor because of this equation here. It's the opposite for a capacitor. For a capacitor, you cannot have a step change of voltage, but you can have a step change of current, okay? And that's because for an inductor, V is equal to L di dt. For a capacitor, I is equal to C dV dt. Okay. All right. So that is an example of solving an RC circuit using the initial and final values. So we'll continue with this next time. But for now, we're going to end. In closing, check out the pre-lab, which is due Thursday. You'll have the lab this Friday. And then also check out the upcoming assignments. Thanks for joining class. If you would like to stick around for office hours, please do so. I'll start those in a few seconds. If not, I'll see you next time. Have a great night.